Kia ora and welcome. This is the final webinar in our mini-series to showcase some of the recent developments in remote sensing technologies and how we use that to apply to answer questions for policymakers, councils and landowners. Today's topic is landslides, erosion and sediment, or more particularly, how to use remote sense data to predict and mitigate those events, keeping soil on the land and preventing sediment delivery to streams. Raphael Spiekermann is a geomorphologist with Manaki Whenua and is nearing the completion of his PhD as part of the Smarter Targeting of Erosion Control MB program. Hugh, who's staying in the background for this but will help us out with the Q&As, is the research leader for erosion processes and management at Manaki Whenua and co-leads the Smarter Targeting of Erosion Control program alongside Chris Phillips. Over to you, Raphael.
Thank you, Christine. So good afternoon, everyone, and welcome to this final talk from remote sensing webinar, which is focused on geospatial landslide modelling for targeted erosion control. So what we're presenting today is a summary of research undertaken in the past 3 to 4 years. As Christine mentioned, it's been funded largely by the MB Endeavour program, Smarter Targeting of Erosion Control. And in this talk, following a brief intro, we'll touch on data acquisition using remote sensing to rapidly build landslide inventories, also on implications of spatial scale of remote sensing products. But then the focus of this talk is on adding value to those remote sensing products through statistical landslide susceptibility modelling from regional all the way down to tree scale. So I'll then aim to illustrate how the models can be used as decision support for land management before wrapping up with some key takeaway messages. Now, the science in this instance has a very applied context. Our objective is to support the design and implementation of cost-effective targeted erosion control measures to meet national water quality targets. And so we've been acquiring data to develop models that make the connection between catchment erosion sources, sediment loads in rivers, and sediment-related water quality. Another key motivation is to develop methods to quantify the performance of erosion control across multiple spatial scales. So in the context of freshwater farm plans, for instance, we need to identify sediment-related risks and attempt to mitigate those risks. But then the question is to what effect, how effective has previous mitigation been, and what can we expect from current and future tree planting? So these are some of the research questions we're trying to respond to. Now, to begin with, I wish to, on this slide, stress just the significance of imagery resolution when building inventories of any kind of mass movement process. First of all, it's important to consider the geomorphic process involved and the potential objective of the mapping exercise. Now, for example, we need to distinguish between the landslide scar and the landslide deposit. Now we can see in the graph to your lower left, it's showing a typical size distribution for rainfall initiated shallow landslides in hill country terrain. So it's frequently the case that the average scar size of these landslides is less than 100 square meters, as you can see in the graph. Now you can see in the World View 2 image above that this imagery is very well suited for mapping features of this size. The ground sample distance or pixel size is about 0.5 meters. Now when we contrast this with a Sentinel-2 image, where a single pixel is the equivalent of an average scar size, while the imagery is freely available and well suited for initial examination of region-wide impacts, for instance, it's less suited to comprehensively mapping individual shallow landslides and separating out scars from tails. Now, over the past few years, we've built landslide inventories by mapping from high-resolution imagery, such as WorldView and Pleiades satellite imagery. So we now have inventories consisting of significant landslide triggering rainfall events, shown in the top row of those figures, as well as multi-temporal records that span more than 50 years, you can see below from D to F. Now, we've also compared manual versus semi-automated mapping techniques and quantified implications of rapid mapping techniques on the performance of statistical slope stability models. And similarly, we've considered the pros and cons of event versus historic records for landslide susceptibility modeling. So this piece of work has been published in Geomorphology last year, and if you're interested in this subject, we'll be sure to make it available to you. Now, in terms of the semi-automated mapping approach that we use, it's commonly referred to as object-based image analysis. So usually orthophotos or satellite imagery is used, whereby the image, as sort of illustrated in this image, is segmented into uniform or homogeneous image objects. And then these objects can be classified based on a rule set that usually includes topographic variables, for example, slope gradient and indices derived from the imagery itself. So this process can greatly increase the efficiency of mapping because no digitization is required. The boundaries of the features are determined by the segmentation algorithm. So what do we use these landslide inventories for? Well, the primary use is to develop statistical landslide susceptibility modeling and models that predict the future locations of landsliding. So shallow landslide susceptibility can be defined as the likelihood of future landslide occurrence for a given aerial unit, such as a pixel, given local environmental conditions, with our focus here on rainfall-triggered shallow landslides, which is the most widespread base movement process in New Zealand. So the method in its basic form consists of extracting spatial data for both landslide locations and randomly generated non-landslide locations. Typically, we include spatial data that are known to influence slope stability, for example, slope gradient, land cover, and rock type. The models are trained then to predict the likelihood of landslide occurrence for each grid cell. The model output is a probability value that can range from 0 to 1, which is the probability of that unit representing a future site of slope failure. So the values close to 1 are likely to fail at some point in future, whereas values close to 0 are stable or unlikely to be sites of future landsliding. Now the model predicts where landslides will occur based on past observations, not when they will occur, which is an important point of difference. Now this map is an example of a regional scale assessment of landslide susceptibility, in this case for the Horizons region, that draws on our large database of shallow landslides and nationally available data sets, such as the Land Cover Database of New Zealand, that are then used as explanatory variables in the models. Now you can see the value of these regional scale maps is that you can immediately identify where the hotspots are within the region, accounting for variation in lithology, topography, and land cover. Provides an objective basis for prioritization of resource for mitigation, which is an improvement on previous products such as the highly erodible land model. Now, I'd like to discuss how different data products available at different scales can serve different purposes to support decision-making for land management. Now, other issues determined by the scale of data used for modeling include its impact on the accuracy and performance of models, as well as requirements of computing power. So as we begin this journey through the hierarchy and scale, I'd just like to draw your attention to the left tab, where I indicate in the red the scale we're considering on each slide. So we can see here the 15-meter National Digital Elevation Model, which many of you I'm sure are familiar with. It's based on topographic contour lines. So at regional scale, it informs very well on the morphology of the land surface. So we can identify the Rimutaka Range and the beginning of the Tararuas and the Eastern Wairarapa Hills here, for example. Similarly, the Land Cover Database of New Zealand is a fantastic multi-temporal resource that covers the entire country. Again, a data set we draw on for landslide susceptibility modeling as it reflects the varying influence of different types of land cover and vegetation on slope stability. All right, so now let's zoom in to the Wairarapa Hills to consider what a landslide susceptibility model based on these data looks like. Now the probability values here have been classified into 5 classes, which we can refer to as low through moderate to high landslide susceptibility. So areas of orange and red is where we would expect future rainfall triggered landslides to occur. As we saw for Horizons, this scale is great for identifying hotspots of both high and low. The central area in the blue, though it's steep topography, is not as susceptible because of the limestone in that area. So we'll now zoom into that red rectangle to take a closer look. Now this orthophoto shows the extent of that red window shown in the map to the right. So you can see the black farm boundaries in this case. This is just to give you a sense of the scale we're at. On the left you see we've moved from regional down to farm scale. Now the same model looks like this. We can see at farm scale there is again great variation within and between farms. And what I'm going to do now is show on the next slide the same model, but now substituting the topographic variables derived from the 15-meter digital elevation model with those from a 5-meter LiDAR digital elevation model. So it's an increased resolution, and you can recognize a much enhanced spatial refinement of the model predictions at 5-meter resolution. So use of LiDAR-based digital elevation models significantly improves the model's ability to correctly classify landslide versus non-landslide locations. It's something we quantified. So average classification accuracy increased from 72% to 88% for the model using 15-meter digital elevation products versus the topographic variables derived from the 5-meter digital elevation model. Right, so now I'd like to select a farm. You can see it outlined in blue to demonstrate what the implications are at farm scale. So here again, the susceptibility model based on the 15-meter digital elevation model. Now just for this farm, we can see great variation in susceptibility, yet we don't really get a sense for what the topography looks like here. In contrast, the use of the LiDAR-based model at an increased resolution clearly provides the detail required at this farm to slope scale. This comparison of model results demonstrates the value of access to high resolution topographic data for modeling landslide susceptibility that can then be used to support better targeting of erosion control at this scale. But I'd like to now consider an issue with the typical hill country farm and what it means for slope stability modeling. When we look carefully at this orthophoto, what do we see? There are many widely spaced trees located across the slopes, and this is typical of a silvopastoral system in hill country where the land manager seeks to balance pasture production and slope stability as well as other beneficial outcomes of trees such as shade and shelter for livestock. And this is how the land cover database maps this area. So we see different types of vegetation cover such as grasslands in that light shaded green color, deciduous hardwoods and also some carnica. But for pastoral farms where many individual trees are spread throughout the landscape, national or regional scale data are inadequate. The effect of the individual trees is not captured, and that's important if we wish to know the effect of the trees and also future tree planting in these silvopastoral landscapes. Now, LiDAR data enables individual trees to be identified. We can also broadly classify these tree canopies using high resolution imagery. So in this instance, we have 4 classes showing eucalypt, carnica, poplar willow, and coniferous species. So we then developed tree influence models on slope stability, which represent the influence of individual trees as a function of distance from tree at 1 meter pixel scale. So these tree influence models can be included in landslide susceptibility assessments to then quantify the effect of the trees at farm scales in pastoral landscapes. So again, I'd refer you to this publication for further details on the methods and results relating to the tree influence models and slope stability, which we'll make available to you. But now this is the resulting map using LiDAR data at 1 meter pixel scale. In this instance, the effect of all tree cover has been removed. So what we're looking at is a treeless pasture-only baseline to landslide susceptibility. Now, when we add the trees back in through the use of the tree influence models of slope stability, we can quantify the change in slope stability due to the individual trees. And so this map now shows which areas have been successfully stabilized due to tree planting and pre-existing vegetation, as well as informing on where additional erosion control would be required. You can see examples of that in the white circles. And if we now look at the orthophoto, it confirms that these areas are steep slopes. without tree cover, and a field visit would perhaps verify that. Now, this work represents a world first in terms of statistical landslide susceptibility modelling at the scale of the individual tree. And again, I refer to the published journal article, which we'll make available to you for those who are interested. Okay, so now our interest is not only in locating the future sites of landslides, but to link hill slopes to streams and consider the likelihood of sediment delivery to a stream in the event of a landslide being triggered at any given location. So you can see in this photo, for instance, that some landslides clearly deliver sediment to the stream channels and others do not. And so we developed a statistical landslide connectivity model using a set of 2,000 scars and 1,200 debris tails from the 1977 storm event in the Wairarapa. And because it's a different topic, the use of different colors, the landslide connectivity map shows the probability of sediment delivery to the adjacent streams. So landslides triggered in the brown zone are unlikely to deliver sediment into the streams and much more likely in the blue zones. Now this map can be integrated with this prediction of landslide susceptibility, which I was showing previously, to produce this map showing the potential sediment delivery from landslides. Now the red class, the high, shows the high potential, or where the high potential for sediment delivery is within the map or within the farm. And it's the class we're most interested in from a sediment mitigation point of view, since this is not only where the landslides are most likely to be triggered, but also much more likely to deliver sediment to waterways. So this map shows the spatial predictions under pasture. Again, it's a treeless baseline. And the consideration of connectivity has approximately halved the area of slopes that require treatment compared to the landslide susceptibility map on its own. And let's now add the trees back in to examine the change due to the tree cover. So trees on this farm have made a significant difference to potential sediment delivery. In fact, we quantified it for this farm. It's about a 40% reduction in sediment derived from landsliding. And the photo of the farm shows the extensive tree cover across the slopes. So effectiveness is mainly a function of adequate tree cover on slopes representing future sediment source areas. Because of the LiDAR data, we can say that these sediment source areas make up a fraction of the farm area. We made predictions for 50 such farms and found that on average, only 5% of the land area accounts for approximately 2/3 of potential landslide-derived sediment. In fact, we also undertook scenario modeling to quantify targeted versus non-targeted planting and found a 10-fold increase in cost effectiveness of measures. So prioritizing these areas is important, which is what I'd like to illustrate on the next slide before wrapping up. I'd like to demonstrate here what targeted versus non-targeted erosion control means and what the implications are. So if you look at the orthophoto in the top right, what do we see? We see a large number of trees, mainly poplars and willows, with a eucalyptus grove labelled on the right. The same grove is shown in the photo below for your reference. Now, based on this view alone, one could easily conclude, okay, tick, job well done. But now let's look at the landslide susceptibility maps for the same area. The map on the top left is what the landslide susceptibility would be without any trees present. Again, a pasture-only baseline using 3 classes, low, medium, and high. We know the vast majority of landslides are triggered in the red zone. You can see the area where the eucalyptus grove has been planted, it's very red. So it's where we would expect landslides to occur if no trees were present. Now the lower map shows the same landslide susceptibility classification, now including the influence of the trees depicted in the orthophoto above. Now the slope with the eucalyptus grove is mostly changed to green, so it's being stabilized. So it provides quite a nice contrast to the poplars and willows to the west, which are primarily located on lower slopes or valley bottoms where landslides are unlikely to occur with or without trees. That's why there's very little change to the extent of the red zone in that part of the map. Now, when we include the connectivity model to consider the potential for landslide-derived sediment delivery to streams, a similar story is shown here, although some of those steep upper slopes are no longer red. It just means they're unlikely to be sediment sources because landslides triggered there are likely to deposit on slopes rather than into the adjacent streams. This work on integrating landslide susceptibility and connectivity is currently in progress with ecological engineering, and once it's online, we'll also make it available to you. Okay, so to summarize this talk, we've aimed to illustrate how different remote sensing products and spatial data sets can be used to inform landslide erosion and sediment control. And we discussed how the difference in scale are complementary in this process, beginning with national available data sets, finally considering the benefits of LiDAR data for improving both model performance and spatial refinement predictions. Some of these benefits include the ability to capture individual tree effects on slope stability and quantifying the effectiveness of trees in terms of reductions in future landsliding and sediment delivery. And to give you 5 key takeaway messages. First, I'd like to reiterate that remote sensing techniques enable rapid acquisition of large quantities of landslide data, comprising tens of thousands of individual landslides per event in some cases. These data are essential for building models. Statistical landslide susceptibility modeling provides a data-driven approach to better target erosion control from regional all the way through to paddock scale. The third point would be that LiDAR enables new high-resolution data collection and analysis, including, as we showed, individual trees. Again, it increases the accuracy and the refinement of the spatial predictions, and it can be coupled with the statistical connectivity model to mitigate and target those sediment source locations. And finally, land management scenario modeling indicates targeted mitigation results in a 10-fold increase in cost effectiveness of measures. And with that, I'll hand back over to Christine and hope there's still some time for questions.
Thanks, Raphael. And yes, indeed, we do have some time for some questions, and we have some. But first of all, what do you see the opportunities for this work going forward? You know, obviously future research is of interest to us, but also, you know, the application of this work out there with our stakeholders and regional councils and so on.
Yeah, I think I mean, that's a good question. I see clearly opportunity both for research and application. Perhaps in terms of research, we're currently using rain radar data to control for the triggering mechanism, and that can improve the spatial predictions and also enable landslide forecasting in pastoral hill country. And yeah, also in terms of application, I mean, we'd like to see regional applications of landslide susceptibility to, as we show, improve cost effectiveness of erosion and sediment control within freshwater farm plans, ideally in hill country. And finally, I would also say we see real benefit in the ability to quantify the effect of tree planting on landslide erosion and sediment delivery for farm, but all the way through to regional scales. So that could also be part of a future monitoring program.
Great, thank you. And perhaps a bit related to the application piece with the STEC program, the Smarter Targeting of Erosion Control, have we got particular advice on what are the practical options for stabilizing in these susceptibility hotspots?
Yeah, I mean, so depending on the erosion process involved, obviously, this talk's really focused on shallow landsliding, which is a dominant process in much of the soft rock hill country across the North Island in particular. But early on in the project, Chris Phillips, my colleague, wrote a couple of comprehensive reports outlining best practice methods in New Zealand, and also benchmarking that against the international literature. So there was input from our colleagues overseas, and yeah, perhaps those reports could be a useful guide in terms of identifying best practice depending on the erosion process and the setting. So perhaps it's something we could also make available following this talk.
Great, thank you. Another tree question. What method did you use for the classification of tree species in your tree layers?
Support vector machine learning was the method used as the classifier. And we'll go into a little bit more detail. So we used the regional orthophotos available at Wellington Regional Council from 2010, 2013, 2017, and from 2013-17 they include the near-infrared band. So the method basically involved delineating individual tree crowns using the canopy height model from the Greater Wellington Regional Council. It's 1 metre resolution, so an automated procedure to delineate the individual tree crowns, and then characterising those tree crowns using this multi-temporal set of orthophotos from the Greater Wellington region, and then training a model using data obtained in the field on 2 farms. We mapped about 10,000 tree crowns and classified those trees, and that data was then used to build a model to classify the tree crowns throughout the Wairarapa Hill Country. So in brief, but I mean all the detail is also provided in the paper I referred to.
Great, thank you. Trees are our hot topic today. How is the effect of individual trees on stability quantified? Is it based on root depth?
Yeah, so it's not in this instance. So there's generally a lack of data, root data, especially related to widely spaced trees in these silvopastoral systems, and also trees of different ages and species. And that was the dilemma leading into this work, is how do we represent that influence spatially of the individual tree? And I used a method which builds on a method by John Diamond, where an empirical approach is used by considering the spatial relationship between where landslides occur in the landscape and where trees are located. And over a very large study area using 43,000 shallow landslide scars that were mapped, I created a relationship by considering that spatial relationship between the fraction of ground eroded and distance from tree. And that provided the rationale for the tree influence models and slope stability, which I was showing on one of the slides. So it's not a physical approach to like a root reinforcement model, for example, but it's just an empirical approach using to develop that relationship and represent that influence of the trees to then integrate it into the landslide susceptibility model. And the effect of the tree is then quantified in the landslide susceptibility model through logistic regression, which is the method we used here, to get at the effect size of the trees in terms of determining slope stability. Yeah. So it's somewhat complicated, and there are 2 phases to it, but yeah.
Sorry, I didn't mean to ask such a complicated question. I think, look, we've got time maybe just to fit in one more question. And that is, apart from satellite data, do you use ground-based sensors and other information, which is then processed with the satellite data?
So for mapping, so classifying the trees, we did use training data that was gathered in the field. So mapping the individual trees and labeling trees according to their species. But the mapping of shallow landslides is all done remotely using high resolution satellite imagery.
Great. Look, we've got a few other questions that we will respond to directly and share with our audiences when we put the presentation up on our website. I'd like to say a huge thank you to Raphael and Hugh in the background there for this great presentation. I think it will have triggered a lot of further questions and conversations, and we'd be really pleased to keep those going. This wraps up our little mini series of remote sensing webinars for now, but there's more work in this space, and you will find this this topic pops up in future Link online webinars over the rest of the year. So watch this space for more. And at this stage, a big thank you to everyone for joining us for these last 2 days. Thanks.